All right, as we move into chapter 3, or our next chapter, we're going to start talking about something called atomic theory, which basically deals with what an atom is, how it's classified, how we can use it to understand things about different elements and different compounds. We're also going to talk about the periodic table and kind of introduce the periodic table a little bit. So this is our shift into more of the chemistry or intro to chemistry side of our class. So we're going to start with the most basic units, which is called the atom. So we're going to go all the way back here to the very, very first or very early atomic theories. So when we say atomic theories, we're talking about different theories about the atom, right? What historical scientists thought about it and how they kind of talked about it. So the first one we're going to talk about is this picture of this guy named Democritus. Democritus basically gave the idea that atoms are tiny particles of matter that cannot be broken down, and he said cut, but basically cannot be broken down any further. So he said once you reach the point of having this atom, we can't break it down into smaller parts. It's just the atom itself. Now today, we know that atoms are made of even smaller parts, protons, neutrons, and electrons. But at the time, they didn't understand that, right? They thought that an atom of oxygen was as small as it was going to get, or an atom of lead, once you got down to that single atom, that was as small as it could get. And so today we know there's even smaller parts that make up the atom, but at the time that was the thought process, was that you get these tiny particles of matter that you can't break down any further. So that was kind of the first theory. A guy by the name of John Dalton came along later, and he really kind of changed his atomic theory, not just based on thoughts, but based on experimental findings. And his theory on the atom is pretty close to what we use today, or what we call modern atomic theory, which we'll go over here in a little bit. But his he put together kind of a list of properties of atoms, and most of those are still really true today. So we'll go over that here in a little bit. But he was really the second one to give us a major new theory on the atom, and we'll look at that in a little bit. Okay, and so as we start looking at the atom and what the atom contains and what different things are made up of, we start discovering that atoms are not just the smallest part, that actually there are smaller things contained within an atom. And so the first thing that was really discovered out of the 3 subatomic particles, right? When I say that word, subatomic particles, subatomic, that just means smaller than the atom, right? There are subatomic particles that you guys have probably heard of, called protons, neutrons, and electrons. And so the first of those subatomic particles to be discovered was called the electron, right? Or it was the electron. And it was discovered by a scientist in the name of J.J. Thompson. Okay, that's something that we want to make sure we remember. J.J. Thompson did an experiment with metals, and he found out that no matter what type of metal he worked with, it was giving off this negative charge. Okay, I hope by just the background knowledge of what we know about electrons do give off a negative charge, right? Electrons give off a negative charge. And he found out that all of this negative charge was coming from each different type of metal, no matter what. So he made the conclusion then that all of these particles called electrons have to be found in every type of element, and every type of atom probably then has these electrons. Okay, so he called them electrons. When I write electrons, I'll most of the time just write an E with a little minus sign, right? E to represent the word electrons, and minus to represent the fact that it has a negative charge, right? So once he discovered, or once he kind of concluded that all atoms contain electrons, he kind of started in making this model. Okay, it's called the Thompson model of the atom. And what he thought was these negatives are just kind of dispersed evenly throughout the atom, right? There's all these electrons in an atom, and they're dispersed evenly throughout the atom. Now, this is not what we know the atom looks like today, but this is one of the first atomic models that was really given, right? And it's called the Thompson model. So after the Thompson model and after J.J. Thomson's experiments that told us, well, we've got these negatively charged particles called electrons, scientists really started diving into, well, are there other small particles that can change the way an atom behaves? And so a guy by the name of Ernest Rutherford, that's a name that we need to know as well. He conducted an experiment, and his experiment is called the gold foil experiment. And I'm going to explain the experiment here in just a minute. But it's called the gold foil experiment. Okay? So Rutherford conducted this gold foil experiment that eventually led to the discovery of the nucleus. Okay? And what we know about the nucleus of an atom is that it's contained in the center, right? And it contains two different subatomic particles, the protons and neutrons. But his experiment went something like this. He shot what are called alpha particles through a thin foil made of gold. Okay, he had a device that shot out these alpha particles through gold foil. And what an alpha particle is, it's important that we understand it's a positively charged particle that is 4 times heavier than hydrogen. Okay, so the heavier part, that doesn't really make a difference to us, but it does affect our thinking to know that these alpha particles are positively charged. That does make a big difference. So he shot these little particles through a sheet of gold foil. And it was expected that the particles would pass right through the foil with really no deflection, right? Deflection means they would bounce off in a different direction. So his expectation, based on the Thompson model, right? If we remember what the Thompson model looked like, it was a circular atom with pluses and minuses evenly dispersed throughout that atom. So there's not an area of positive or negative. There was just evenly dispersed positive and negatives throughout the atom. And so his expectation was, if I've got a positively charged particle, it's going to pass right through that gold foil and right through those atoms. Okay, so here's what he expected to happen, right? Here's the Thompson model, evenly distributed positives and negatives, and he thought his little positively charged alpha particles, the green one, he thought it would pass right through these atoms with no problem. Okay, here's what his experiment looked like in a kind of basic sense, but here are the alpha particles leaving this radioactive source, going through the gold foil. Now, here's what actually happened in the experiment. The expectation was that most of them would go directly through it with very little deflection. But in reality, what happened is that some of them were deflected quite a long way the second they hit the foil, right? They were deflected. So I want you to think about what would cause a positively charged thing to be deflected. Would a positively charged particle be deflected by another positively charged particle, or would it be deflected by a negative particle? What do we know about positives and negatives? Right? Positives and negatives attract, but positives and positives repel each other. Think about like a magnet, right? If you put two of the same sides of a magnet together, they don't attract, they repel. So if you have a positively charged particle hitting another positively charged region, those two things would repel one another, or they would deflect one another. And so this is really what happened, right? We saw an alpha particle, this green, come in and hit a positively charged region of the atom and deflect. right? Just think about if you put two wrong ends of a magnet, they're going to bounce off each other. That's exactly what happened here. So Rutherford then concluded that since most of them passed right through the gold foil, but some of them changed directions, he concluded that there has to be a small and positively charged region at the center of the atom. Okay, at the center of the atom, he said there has to be a positively charged region that was causing my positively charged alpha particles to deflect, okay, or to be repelled. And so he called that densely positive region the nucleus. Okay, he called that region the nucleus. From there, his suggestion or his thought about the electrons is not that they're evenly distributed throughout the rest of the atom, but that they orbit the nucleus similarly to how planets orbit the sun, right? They follow this path around the outside of the nucleus. And I'll show you a picture of what that looks like here, but that's basically opposite of what the Thompson model said. The Thompson model said electrons were spread very evenly throughout the atom, but Rutherford, on the other hand, is suggesting that these electrons are not spread out evenly, they're orbiting the nucleus. And if they're orbiting the nucleus, that means most of the volume of the atom is just pure empty space. Okay, I'll show you here what that picture looks like of the Rutherford model. But his model says we've got a nucleus in the middle with electrons making orbits around the outside. His model was also called the planetary model because it looked or reminded people of how planets orbit the sun. Okay, so you'll need to know here what the Rutherford model looks like. Here's what it looks like. This is a very kind of typical clip art version of an atomic model, and it's very popular for what people think of when they think of chemistry and of the atom. But in all reality, we know that the atom doesn't truly look like this. Like today, we know it doesn't look like this, but this is what the Rutherford model looked like. So you've got the nucleus here in the center, and all he knew about it so far was that it is positively charged. Right, that's all he knew about it at this point. And then he said, we've got electrons here in orbit. And so if I've got an electron orbiting on this path right here, I've only got one electron in that orbit. So in all reality, the rest of this really is empty space. Right, there's my electron in orbit. And if I've got an electron on this path, that means the rest of this is empty space. Right? The rest of that path is also empty space. And if I've got an electron orbiting on this path, right, somewhere in the middle there, that means the rest of this is empty space. So when we look at the atom and the model that Rutherford did conclude with, it's a lot of empty space, right? Those lines make it look a little bit more crowded, but in all reality, that electron is only in one location at one time. And so the rest of it really is pretty much empty space. And so most of those alpha particles that he shot through, ones that we looked at in the drawing, most of those alpha particles did have plenty of room to shoot right through, right? But the ones that hit the nucleus then redirected and went in a different direction. Okay, so that's the Rutherford model. So he came up with this planetary model, and he really formulated the idea for the nucleus itself. All right, so I want us to think back now about we've discovered by Thomson the fact that particles have electrons. They have negatively charged particles. And now Rutherford has discovered, well, there's some positively charged particles in the center of the nucleus as well, in the center of the atom as well. So he kind of concluded that since most atoms in general are neutral, let's think about what neutral means, right? Neutral means that they have an overall charge of 0, right? The positives and the negatives have to equal each other. That's what neutral means. So if our atoms are generally neutral, there must be positive charges to offset the negative charges given to us by the electrons, right? Thomson told us there's electrons in the atoms. Rutherford figured out, well, there's a positive region, and so he concluded, though, that positive region must be made up by something called protons, and he named them protons. Okay, and when I abbreviate protons, or when I write out protons, I like to make a P with just a little plus sign, right? P plus for protons because they have a positive charge, and an E minus for electrons because they have a negative charge. Okay, so he concluded we've got now these positives and these negatives that help contribute to make a neutral atom, right? Neutral means that my positives and my negatives cancel each other out, right? My atom would be neutral if I had 10 protons and 10 electrons. That would make a neutral atom. They cancel each other out. Okay, then his additional conclusion said, since electrons have very little mass, right? That was part of Thomson's discovery, was the mass of an electron. It's very, very, very small. So he says, since we know electrons have very little mass, there's got to be another particle present that makes up some of the mass of an atom, but doesn't affect the charge of the atom. Okay, so what particle do we know adds to the mass, but doesn't add to the charge? And we know that that is a neutron. Okay, that's a neutron. Neutrons contribute to the mass, but not the charge because they have a neutral charge. So when I need neutrons, I just write an N. Sometimes you'll see an N with a little 0 up at the top. I don't usually write it like that, but you might see it because it's 0 because it's neutral. All right, so today we kind of put all of this information, and Rutherford started putting together this information, but we know that the nucleus is made of two of the kinds of particles we've talked about. The nucleus is made up of both protons and neutrons. That's really, really important. We know that in the nucleus, we have both protons and neutrons. Okay, protons have a positive charge, and neutrons have a neutral charge, which means the nucleus itself is positively charged. Right? Because we know that the electrons are not located in the nucleus. So the only thing that's found in the nucleus that contributes to the charge are protons, and then the neutrons help get the rest of the mass of the atoms, but they don't affect the charge. So the nucleus itself has a positive charge. Okay, protons, an individual proton has a positive charge and a mass of 1 AMU. And AMU stands for atomic mass unit. Okay, so protons have a positive charge and they equal 1 AMU. Neutrons have no charge and a mass of 1 AMU, which means protons and neutrons have the same mass. Protons and neutrons have the same mass. They weigh the same. In the nucleus itself, protons and neutrons are held together by strong, strong forces called nuclear forces, right? Nuclear forces because they are found in the nucleus. Okay, they're held together, even though positives and neutrals don't normally attract each other, right? It's usually positives and negatives that attract. But in the nucleus, we have something else going on called nuclear forces that hold those protons and neutrons together. All right, and then last thing here I want you to kind of look at is that an AMU, or the mass of one proton, is equal to the mass of about 1,800 electrons. So a single proton weighs the same as 1,800 electrons. And so when we think about the mass of a single electron, it is so insignificant in comparison to the mass of protons and neutrons that the mass of the electron is ignored when we find the mass of the atom. So that means when I'm trying to find out how much a single atom weighs, I do not count how many electrons it has. That does not affect my mass at all. The only thing that I am looking at when I'm finding how much mass an atom has is how many protons plus how many neutrons that atom has, and that gives me the mass of my atom. I do not count in the number of electrons when I'm looking at my mass, because the mass of the electron is so small and insignificant, it doesn't count. All right, so we've talked about older atomic theories. Now I'm going to walk you through the 5 principles of what we know about atoms today. Okay, or otherwise it's called modern atomic theory. Okay, so John Dalton put out a new atomic theory that's similar to what we know today, but it's got a couple changes. And so what I'm going to lay out for you is what we know about the atom today. All right, number 1, all matter is composed of small particles called atoms. All matter is composed of small particle called atoms. Now, we know atoms are made up of even smaller parts, protons, neutrons, and electrons. But in order to really have the properties of its element, it's got to have them composed in a certain way that makes them an atom. So any matter that we're talking about, oxygen, nitrogen, carbon, any compounds we know, water, whatever it is, all of that is made up of atoms. Okay, number 2, atoms of one element differ in properties than that of another element. And so when we start looking at elements, we look at the periodic table and we say, elements like oxygen. Every oxygen atom is different than every carbon atom, right? These two atoms would not behave the same. They would not look the same. They would have different properties. They would have different things about them that make them who they are, right? So oxygen has a certain number of protons, neutrons, and electrons, and that number is different than carbon. So what we're saying is that elements are very different from one another, okay? Oxygen atoms look, act, behave different than carbon atoms, and carbon atoms look, act, behave different than sulfur atoms or nitrogen atoms or whatever element you're looking at, but they look different. They have different properties. Okay, number 3, atoms of the same element always have the same number of protons, but may vary slightly in their mass. This one is probably the most important part of the atomic theory. Atoms of the same element always have the same number of protons. I want you to underline that, highlight it, whatever you need to do, but they always have the same number of protons. They might vary slightly in their mass. So what that means is that we're going to talk about how we determine the number of protons, neutrons, and electrons in an atom next class, but I want you to look at oxygen, for example. Okay, oxygen has 8 protons. Okay, if an oxygen atom has 8 neutrons, it would behave a certain way. There might be another oxygen atom that has to have 8 protons, but maybe it has 9 neutrons. It would behave slightly different than that version of an oxygen atom. But the thing that makes it distinctly oxygen is that it has 8 protons. If it adds a proton and moves up to 9 protons, it's no longer oxygen, it is fluorine. It's a completely new element. So the number of protons that an atom has completely makes its identity. Okay, the only way we know for sure what type of element we're dealing with is the number of protons in that element. Okay, the number of neutrons, which affects their mass, that number can change a little bit. But the number of protons in a particular atom cannot change. If the number of protons changes, then the element changes. Okay, so you might see things written like this. If I'm dealing with calcium has 20 protons. Calcium atom might have 20 neutrons. Let's say I add a neutron, but nothing else. I still have 20 protons, 21 neutrons, which means this atom right here is still calcium. Okay, but let's say I took away a proton and I'm left with 19 protons and 20 neutrons. Is this atom still calcium? No, it's not. This atom would now be potassium. Okay, and so you guys, we still are going to start looking at the periodic table so you'll get familiar with how I'm figuring these out. But I really need you to understand that if these atoms are coming from the same element, they have to have the same number of protons. That's what makes an element a certain element. All right, number 4, atoms of different elements can have different average masses. So that means all that's saying is that oxygen atoms are going to have a different mass that does not equal fluorine atoms. And fluorine would have a different mass that does not equal neon atoms, right? And that's pretty self-explanatory. I think if you have atoms of different elements, it should make sense to you that they weigh different things, right? Because they're not the same. They weigh different. All right, number 5, atoms cannot be broken down into smaller particles in ordinary chemical reactions. And so what we're saying here is that we can't break an atom into its protons, its neutrons, and its electrons in ordinary chemical reactions. That's important. Ordinary chemical reactions. It can be done. We can make things or make situations in which electrons start coming off and protons get separated, but it's not in an ordinary chemical reaction. It's in a pretty extreme lab space. So when I mix two things together, I'm not breaking them all the way down to their protons, neutrons, electrons. I'm just mixing atoms. So the atoms themselves are pretty stable. When we start breaking into protons, neutrons, and electrons, it's in a pretty extreme lab space. So for all of our intents and purposes right now, atoms, we don't break them into our smaller particles. We know they're there, but we don't break them into the smaller particles. So here's the definition that I would like for you to have down for what an atom is. An atom is the smallest particle of an element that retains the chemical properties of that element. That's super important. It's not the smallest part of an atom, because that would be an electron, right? An electron is the smallest part of an atom and the smallest part of an element. But an electron by itself does not act like oxygen or act like carbon or act like phosphorus. An electron itself acts like an electron. But an atom is the smallest part of an element that maintains the chemical properties of that element. And so it's got protons, neutrons, and electrons arranged in a certain way to give it certain properties. And so I want you to have that definition of an atom down. As we move through the next couple of days of notes, we're going to start looking a lot more at atoms and how we count protons, neutrons, and electrons, and how those things appear on the periodic table as well.